All right. Okay, bonjour. Welcome back to class. So today we will continue the discussion of the Green theorem and the divergence theorem that we initiated last time. So last time we stopped with the following auxiliary result. Now it's an auxiliary result, but actually it contains all the mathematical content of what will be the Green theorem and the divergence theorem. It's visible? Yes. Good. So let's remember the following. We have got a domain omega, and we've got a function. We've got a function on that domain omega, some function f, and we would like to compute the following. We would like to state the following two identities between integrals. So on the one hand, the identities are very similar. If you've got a function f depending on two variables, x1 and x2, if I integrate the derivative in the first direction over omega, I can express it as a curve integral. Namely, I can express it as a curve integral of the function f itself multiplied with the first component of the outer unit normal. I take that product, the function f, and that component of the outer unit normal. If I integrate it along the boundary, that will be the same as integrating the derivative in x1 of the function f over the entire domain. So I've got some domain omega, and I want to integrate. I want to know the integral of the x1 derivative, and I can express it as the integral of f against the first component of the outer unit normal. And completely the same, completely analogously, we have the same identity if instead we take the derivative in x2 and the second component of the outer unit normal. Okay, we will take a look at examples for that, why that is true later. But now let's proceed to the main results, which are the results of Gauss and Green. So we got the following theorem, the Gauss theorem and the divergence theorem. Those are actually the two sides of the same coin. So let omega be a domain in R to the 2, be as in the auxiliary theorem before. Same assumptions. And let's suppose we have got a differentiable vector field f. So we want to take derivatives of the vector field. Then the two main results in vector calculus in two dimensions are the following. On the one hand, okay, I take the integral over omega of the divergence of the vector field. I can express this as the integral over the boundary of f multiplied with the outer unit normal. Here we've got a scalar product. And I take a curve integral of this. That's known as Gauss theorem, sometimes also known as Gauss-Ostrowski theorem, and sometimes only known as divergence theorem. And there's a sibling of that result in two dimensions, which is known as Green theorem. The results look very similar. If we integrate over omega the curl of the vector field, then we can express it again as a curve integral. Again, we integrate something over the boundary, and we integrate the vector field, but this time we multiply it with the unit tangent. That's called Green theorem. named after some person with the surname Green. Those are the two most important results in two-dimensional vector analysis. We will first take a look why those are true. Then we take a look also at some relation to curve integrals. And then we calculate a few examples. Okay, we will first prove the divergence theorem using the two auxiliary results before. So the proof of the Gauss and Green theorem. You use the auxiliary theorems. And it's always a good idea to just write down definitions. So if we then start with the integral over omega of the divergence of f, we integrate the divergence of f over the domain omega. By definition of the divergence, it's the integral over omega of the x1 derivative of f, of f1, that is, plus then the x2 derivative of f2, the second component, okay. But if you have those two terms, you can now use the auxiliary result and express them already as curve integrals. Just straight away. So the first term then becomes, okay, we multiply the first component with the first component of f with the first component of n1, and we multiply the second component of f with the second component of n2, of n. But, okay, if you take a look at this formula now, you see this is just the scalar product of f with the outer unit normal, just the definition. And once we recognize that, we can express it as a curve integral, namely the scalar product of f with n. We just use the definition of the divergence, then the auxiliary theorems, we just plug them in, and then we recognize it's a curve integral against the outer unit normal. That shows the divergence theorem, or Gauss theorem. We can prove Green's theorem completely analogously, just making a few technical changes. But I would like to actually show an interesting connection between the Gauss theorem and the Green theorem. Namely, if you take a look at the integral of over omega of the curl of f, I could just do the same, very similar calculations now. But instead, let's do the following trick. Namely, I can also write it as the integral over omega, well, just by definition, that's del 1 of the second component minus del 2 of the first component. Just writing down the definition of the curl. But that curl is also the divergence of something else. The trick I can use is, okay, that's the integral over omega of the divergence of the following vector field, namely the vector field with f2 and negative f1. I can write this curl of f as the divergence of another vector field. Now I can just use the Gauss theorem. Now, using the divergence theorem, which we've already shown. Okay, it's another curve integral, namely it's a curve integral along the boundary, well, of this new vector field F2 and negative F1 multiplied with the outer unit normal. But now I can multiply this out. I've got the integral over the boundary curve of F2 and 1 minus F1 and 2 Now I can do another trick. I can write this as the integral of, well, let's write it like this. F1 and F2, so my original vector field, multiplied with negative N2 and 1. What's this vector here? If I have the vector negative N2 and N1, the trick is the following. We know that the outer unit normal can be written in terms of the tangent but if I can write the outer unit normal in terms of the tangent, I mean the outer unit normal is obtained from the tangent just by rotating clockwise 90 degrees. That means the tangent can be obtained from the outer unit normal by rotating in the opposite direction. So I can express the tangent also as follows. Negative N2 and 1. If I've got the tangent like this, I can express one always as a rotation of the other. And so in total, putting that all together, finally we get the integral of f against the outer unit normal. Those are all just little steps. So we use the main theorem for the divergence theorem, we use these auxiliary results, and then we used a bunch of little geometric tricks here. You have a question, please? Okay, this is only the two-dimensional curl here. So the entire lecture today is in 2 dimensions only. In 3 dimensions, it's more complicated. We actually come to that. That will be done in a few weeks. So right now, we're talking only about 2-dimensional curl here. And quod erat demonstrandum. Lots of little steps that then together give us the Gauss theorem and the Green theorem. Last time I was also received a question about how the curve integral of a vector field relates to the curve integral of a function. I think now is the right time to make a little comment about that. Let's do the following remark. So we relate the Gauss and Green theorems where we have got the integral of f against the outer unit normal or against the tangent with curve integrals. So let's say we have got an integral over any curve gamma, could be the boundary of a domain, and we integrate a vector field f against the unit tangent. So what is that? That's a scalar product. Just making sure we know what we're talking about here. It's a scalar product. So we integrate a function. A scalar function, along this curve gamma. We would like to relate this to the notion of curve integral of vector fields. To do that, first let's take the definition of what it means to integrate a function. Okay, we integrate over gamma f times tau, and let's do a very small step here. Well, maybe a bit more explicit. F of some parameterization gamma. Okay, that should be from A to B. And the unit tangent at position gamma t. Just writing down the definition of the curve integral. And then we have got this vector, the speed at position at parameter t. So I'm just writing down the definition of the curve integral. And now at this point, I can also write down the definition of the unit tangent. So we integrate from A to B, still the vector field f at gamma t. And, okay, what's the outer unit tangent? You remember it was the tangent, but we normalized it. So we divided it by the speed. And again, we have got this other speed factor here, because it's a curve integral of a function. Just plugging in definitions one after another. And now I see I can get rid of this speed factor. So I see that these terms here cancel out. And what remains is the integral from A to B of f gamma t, right? And then the scalar product again against the tangent. But if I take a look at this formula, then I remember, yes, it's just the definition of the curve integral of a vector field. I see it's a definition of the integral along gamma of f. Just by definition. That's how we have defined curve integrals. So here we've got the vector field integrated along the curve gamma. So I think it's a general observation for the curve integrals of vector fields. The curve integral of a vector field, okay, we have had this definition. You can also express it as the integral of vector field multiplied with a unit tangent integrate along the same curve. So what's perhaps a nice succinct way of putting that? Let's put it like this as a little comment. The curve integral of a vector field is the integral of the tangent component along that curve. Okay, so to say that's the high-level point of view. So, and if you take a look at these formulas long enough, then all these pieces come together. That is a theoretical discussion for now. Before we go to examples, are there any more questions? Just to see that in action, let's do a few calculations. So the curve integral of a vector field is the integral of the tangent component along that curve. So, examples. Okay, we take again a look at the unit ball, just the disk, the two-dimensional disk of radius 1. And that is bounded by a curve. You have seen it before, the curve gamma going from 0 to 2 pi. And for every parameter t, what we get is the cosine of t and sine of t. So we just walk around the unit circle in counterclockwise direction. Let's take a look at the following vector field. F x1, x2 is very simple. It's just x1, x2. So it's the source vector field. If you draw it, it looks like this. Let's take a look at what happens if it integrates the divergence of the vector field, and what happens if we integrate if he takes the curve integral of f against the outer unit normal. On the one hand, he takes the divergence of f Okay, that means we take the x1 derivative of x1 and the x2 derivative of x2. That added together is just 1 plus 1. So we just take the integral of 2 here. We integrate 2 over the unit disk. So what we get is 2 pi. The unit disk has area 2 pi. If you integrate 2 over it, of course, we get 2 pi. Now, on the other hand, let's check that the divergence theorem is true. So if we integrate if we take the curve integral along the boundary of f against the outer unit normal. Well, what is the outer unit normal here? In fact, okay, you can do the calculations. You can use a formula, or in this case, you can actually use some geometric intuition. So in this case, you can just abbreviate a bunch of calculations. It's the outer unit normal at x1, x2. It's just a vector in direction x1, x2. In this case, that's because we work on the unit circle. So it means we integrate x1 against x2, x1, x2 times x1, x2. Which means we integrate along the boundary x1 square, x2 square. Now, since we work on the unit circle, x1 square and x2 square, of course, are just 1. Which means we integrate the function 1. We write it down like this. Alternatively, you can also plug in, for x1, you can also plug in sine of t and cosine of t. Then also you get that is equals 1. In either case, okay, we integrate 1 along the boundary. we integrate from 0 to 2 pi sine of t square plus cosine of t square square root but again, so since sine of t square and cosine of t square, of course, are just equal 1, so we integrate 1 from 0 to 2 pi, and that's obviously the same, 2 pi. Okay, so we have verified that simple example, the divergence theorem. Let's also do an example with Green's theorem. So let's this time use a different vector field. Let's say f equals x1, x2. And let's say it's a bit more complicated, a little bit. The components are negative x2 square and x1. Let's take a look at the integral over omega of the curl of f. Okay, the curl of f. So we take the x1 derivative of the second component, which means the x1 derivative of x1, and we take the x2 derivative of the first component, which means the x2 derivative, and we subtract that. So in total, just plugging in the formula for the curl operator in 2 dimensions. We integrate this here over the unit circle, over the unit disk. Perhaps you can already tell what is the value. Perhaps you can tell already just by taking a look at what we integrate here. But if not, let's try to compute the same value using Green's theorem. So because Green we know that's the same as the integral over the boundary of f against the unit tangent. You can plug in definitions here, or in fact, it will be helpful to just express it as follows, namely, we've learned we can also express it as a curve integral of the vector field itself. Okay. That means we can express it as, it's both the same formulas, no matter, you can use either definition and you get the same thing that you integrate. You get the integral from 0 to 2 pi. The vector field multiplied with the tangent. So in this case, just plugging in the value, taking the definition of the curve. In the vector field, we get the following, namely negative sine square of t and cosine of t. That's f along f at point gamma t. And we get the tangent. And we've seen the tangent before, negative sine of t. If you multiply all this out, so I take the dot product of these two vectors. If I multiply it out, I get the integral from 0 to 2 pi. On the one hand, the cubic power of the sine function plus the cosine of t square. To simplify that, if we take a look at the cubic power of the sine function, if you plot it, it will go up first to 1, go down again, and go up again. And you can see that the integral of this cubic power of the sine function cancels out. Just like the integral of sine from 0 to 2 pi equals 0, the same is true for sine cube, sine to the 5th power, sine to the 7th power, and so on. So the cubic term doesn't matter for the integral. The only thing that remains is then the square of the cosine. Okay, then we need to integrate the square of the cosine. And that's one of these occasions, that's one of these events where we need to take a look at a list of trigonometric identities. For example, there's this cosine half-angle formula. We use the half-angle formula. Which means the following. I integrate from 0 to 2 pi the following, namely 1/2 of 1 plus cosine of 2t. To be super explicit, that's the integral from 2 pi 1/2 plus cosine 2t over 2. Maybe I should write this a bit bigger here. Now, if I integrate the following from 0 to 2 pi 1/2 plus cosine 2t over 2. It looks a little bit complicated, but actually I can simplify it considerably. Namely, if I have this cosine of 2t and let it go over the interval from 0 to 2 pi, wait a second. It will go up and down again, go up and down again. So that integral will actually be 0. So for the integral, that guy doesn't matter at all. You have the integral from 0 to 2 pi. Which is just pi. So we get the same result, fortunately. We get that this integral essentially equals pi. It's point blank. Then see you next week.